Newton's second law of motion, we are going to consider for both the linear motion as well as the rotational motion. So the formula for Newton's second law for linear motion we know is F net is equal to m into a, where m is the mass and a is the acceleration. Acceleration is the rate of change of velocity, which means the formula looks like this: delta v upon delta t, where delta v is the change in velocity and delta t is the time taken for that change to happen. And similarly, we can write corresponding equations for rotational motion. We know in linear motion we have force, so the corresponding term in rotational motion is torque. So we will write the net torque is equal to, now the corresponding term for m in rotation, mass is in linear motion. So the corresponding term in angular motion is moment of inertia. So m will be replaced with I, and a here in F net is equal to ma. This is linear acceleration. So we will replace a with angular acceleration. So the formula looks like this. The net torque acting on the object is a product of I, which is the moment of inertia, and alpha, which is the angular acceleration. Like linear acceleration was the rate of change of velocity, angular acceleration will be the rate of change of angular velocity. And the formula looks like this: alpha is delta omega by delta t, where delta omega is the change in angular velocity. Now, let us try to apply this concept in a particular setup: acceleration of a sphere sliding down an inclined plane. So, have a look at this diagram. This is an inclined plane which is frictionless, and then there is a ball or a sphere kept on this incline. Now, try to think what is going to happen if we release the sphere from rest, how exactly it is going to move. Of course, the sphere is going to roll down the incline. It is going to go in a straight line, definitely. But the question is, while coming down the incline, will the sphere rotate? And how do we answer that? Rotation depends on the surface. If the surface has a friction, only then the ball can rotate. Without friction, no ball or sphere can rotate. So in this case, since the inclined plane is frictionless and we need friction for rotation to happen, so in this case, only linear motion is going to happen. No rotation of the ball will take place, which means as the ball is coming down the incline, it is going to accelerate with a linear acceleration. No rotation is there, so no angular acceleration will be there. Now, in the real world, it is very difficult to get a plane which is frictionless. So, what we can do is imagine an incline where the surface is, let's say, filled with oil. So, let's say the surface of the incline is completely slippery. In that case, in the real world, the ball is going to come down the incline. But since oil has very, very small, very little friction, so the ball might rotate, but it will rotate to a very small extent. But in an ideal situation, if we can get a surface which is having zero friction, then zero rotation will happen, because rotation of the sphere happens only because of the friction of the surface. Now, let us compare this with another situation where it is the same sphere, but this time the inclined plane is rough. In this case, of course, the ball is going to come down the incline, but in addition to the linear motion, it is also going to rotate. So, in this case, when the incline is rough, then both linear motion as well as rotational motion will take place, which means, have a look. So the ball is going to accelerate in a straight line, as well as rotational acceleration will also be there. Angular acceleration is only present because the incline is having friction. And in questions where we do have a sphere kept on a rough inclined plane, how do you approach such questions? And the steps are very simple. Just apply the Newton's second law. But since the sphere is having linear as well as angular acceleration, so we are going to apply both equations side by side. So for the linear motion of the sphere, the equation is F net is equal to ma. And for the rotational motion of the sphere, the expression will become the net torque is equal to I into alpha, where I is the moment of inertia. And finally, there is a third equation which is very relevant and important. There is a formula which connects linear acceleration with angular acceleration. So, what is the relation between linear acceleration A and angular acceleration alpha? So, the formula goes like this: the linear acceleration is a product of r, which is the radius of the sphere in this case, and angular acceleration. So, A is r alpha. So, in the exam questions where we have a sphere which is rolling down a rough inclined plane, we need to apply these three equations. Now, let us analyze all of this in a little bit more detail. Acceleration of sphere sliding down a smooth inclined plane. So, this is the first situation where linear motion is going to happen, but no rotation is going to happen. and linear acceleration is represented by this arrow. Remember the steps, F net is equal to ma and torque net is equal to I alpha. But here in this case, since the incline is smooth, the sphere is not going to rotate. So we are only going to apply F net is equal to ma. But please remember, while using this equation, we apply this equation along the direction of acceleration. What do I mean by that in this case? Since the sphere is moving on this incline and the incline is this, which means the ball is also moving along this direction. And this direction has been represented by this arrow. What it actually means is we need the net force acting on the sphere, but in the direction of the acceleration. I will explain this how to do it in more detail in a little while, but for now, just remember the basic step one is apply F net is equal to ma, but along the direction of acceleration. And there is a step two, and the step two is we will balance forces in a direction which is perpendicular to the acceleration. What do we mean by that? Acceleration is along the incline, which means the sphere is moving along the incline. That is why the net force is also along the incline. What exactly does this mean? We have discussed this in chapter 2. The concept is if there is an object which is, let's say, moving in a particular direction, accelerating in a particular direction, then the acceleration of that same object along a direction which is perpendicular to acceleration will be zero. Let me explain this with a diagram. So let's say we have a box which is moving to the right hand side and it is accelerating, which means there is a net force which is pushing the block to the right hand side. And let's say we are supposed to find the component of acceleration along a particular direction. So let's say if I draw a dotted line, and this is that dotted line about which we have to find the component. Let me explain. So the overall acceleration of the block is A acting towards the right hand side. But if the question asks what is the component of acceleration along this dotted line? So all we need to do is try to break the A into components. So we will need the angle between this red arrow and this green dotted line. And let's say this angle is theta. If the angle is theta, then the component of acceleration along this direction will be a cos theta. So let me write a cos theta is the component of acceleration along this green dotted line. Now consider a specific situation where the angle theta is 90 degrees. So let me write if theta is equal to 90 degrees, which means that this green dotted line is actually perpendicular to the acceleration. Now, since theta is 90 and what is cos 90? Cos 90 is 0. So A cos 90 will become 0. So let's write down A cos 90 is equal to 0. What exactly does that mean? If the object is accelerating in a particular direction, then the component of that acceleration perpendicular to the motion is always 0. The object is moving towards the right hand side. It is not going up and down. And that is why the acceleration in this direction is actually 0. And since F net is always ma, if acceleration along a particular direction is 0, that means the net force is 0 along that direction. So let me quickly repeat. If there is an object which is accelerating, let's say towards the right hand side, then the net force is towards the right hand side. But let us consider a dotted line which is perpendicular to this acceleration, then the component of acceleration along that dotted line will be 0. And if the acceleration is 0, so the net force will also be 0 along that direction. So step 2, which we are discussing, is balance forces in a direction perpendicular to the acceleration. What this statement actually means is perpendicular to the acceleration, the net force is always 0. So imagine we have some forces going upwards and some forces going downwards. They need to cancel each other out because we need the net force to be 0 in the direction which is perpendicular to acceleration. All right, now back to the step one, F net is equal to ma. We need to apply this equation along the direction of acceleration. How do we do that? The steps remain the same. Step number one is always to draw the free body diagram. We need to figure out how many forces are acting on the sphere. So the first force acting on the sphere is the weight of the sphere itself, which is mg acting downwards. And now the sphere is in contact with a surface, which means it is going to experience a normal reaction. And this normal reaction is perpendicular to the contact surface. Normal reaction is nothing but a force which is provided by the surface on the object, and it always acts perpendicular to the surface. And since the inclined plane doesn't have any friction, so friction is 0. Hence, these are the only two forces acting on the sphere. Now, How do we figure out the net force along the direction of acceleration? So the trick to do this is we need to break the forces into components. Now consider mg which is acting downwards. And if we want to find the component of this mg along the direction of acceleration, which is along the incline, and then another component of mg which is perpendicular to the incline. And let's say if I draw a dotted line, so let's say one dotted line goes like this. This is perpendicular to the incline, and another dotted line which is along the incline. Now to break mg into components, we need the angle. Let's try to figure out how much will be this angle. And how do we do that? So consider this mg. If I extend this mg acting downwards, let's create a right angle triangle. So consider this as a right angle triangle. This angle is 90. So this will be theta. If this is theta, then the third angle, this angle is 90 minus theta. And if that angle is 90 minus theta, then this angle, this small little angle will be theta. Let me repeat. One angle is 90, the second angle is theta. So the third angle over here will be 90 minus theta. And then the angle on the opposite side, this one, will be theta. And why is that? Because consider this angle between the dotted line and the incline. This angle is 90 degrees. If this angle is 90 degrees and one part of this angle is 90 minus theta, so the other angle, this one, has to be theta. So this angle is theta. And now, since we have identified the angle, so the component of mg, which is perpendicular to the incline, will be mg cos theta. And the other component of mg, which will go along the incline, will be mg sine theta. And now, if you observe carefully, mg sine theta is the only force which is going along the incline, along the direction of acceleration. And that is why whenever we are applying this equation F net is equal to ma, we will only write mg sine theta, because mg sine theta is the net force acting along the incline. All the other forces are acting perpendicular to the incline. So normal reaction is acting perpendicular to the incline, as well as mg cos theta is also acting perpendicular to the incline. So we are going to ignore n and mg cos theta for now. In step 1, we only need the net force along the direction of acceleration, which is mg sine theta. Hence, we can say the net force is mg sine theta, and mg sine theta will be equal to m into a. And if we simplify this expression, we will get acceleration as g sine theta. And from this point onwards, please remember, if we have a sphere which is sliding down a smooth inclined plane, its linear acceleration is always g sine theta, irrespective of the mass of the sphere. It could be a very heavy sphere or a very light ball. The linear acceleration will always be g sine theta, where g is the acceleration due to gravity and theta is the angle of the incline. So this is the step 1, applying F net is equal to ma along the direction of acceleration. Step number 2, we have to balance forces in a direction which is perpendicular to the acceleration, which means net force is 0 in a direction which is perpendicular to the acceleration. Coming back to the diagram, we have normal reaction going up and mg cos theta going down, and both of them are perpendicular to the incline. So in step 2, we are going to balance n and mg cos theta. So n will be equal to mg cos theta. And while solving exam questions, this step 2 is also very important. So this was the entire analysis for a sphere which is accelerating down a smooth inclined plane. Since the incline is smooth, the sphere was having only linear acceleration, no rotation was happening.